And then I think I've already posted the homework assignment for today. The homework in here is due Friday. So there will be homework 1A, 1B, 1C, and 1D due this Friday. Normally it's just A, B, and C. I collect the homework every week and post that to Blackboard. So scan your, I think I finally got the camera stuff figured out, at least with the audio. It sounds pretty good. The class this morning, the audio is not at all good. This one does a better job of picking up the audio. So again, with the lecture notes, if you are in quarantine, hopefully you can keep up with the class material. So we've talked about signals. Yes, I did. Pretty sure. Yes. So we've talked about different types of signals. We want to talk about, in this chapter, different types of systems. And we are going to concentrate on linear time invariant, which is too long to spell out. So I'll abbreviate that, LTI systems. Almost all of the theory that we apply in this class, all of our transform theory, will apply to these linear time invariant systems. It's a very important class of systems. It's certainly not the only important class of systems. Nonlinear systems are useful, especially in communication theory. We'll see that modulators are essentially nonlinear systems. But all of the circuits we've studied so far in circuits 1 and circuits 2, you guys are in electronics. Amplifiers can be treated as linear time invariant systems. So it covers a wide class of useful systems. And we'll use this notation for, we've got an input X. And this class will deal primarily with systems that have a single input. You know, it might be a voltage, might be a current if it's a circuit, but we'll often call it X of t. And then the system, the circuit, does some sort of transformation. Transforms the input into an output signal. Okay, and we call that transformation, let's just use this capital letter T to denote that transformation. Now, typically when X of t is the input, we'll call the output Y of t. Okay. Now, what we want to work on today is actually being able to understand what are the properties of a linear time invariant system. What does it mean to be linear? What does it mean to be time invariant? We'll also look at some other properties, okay? We're interested in whether or not a system is stable. We'll be interested in whether or not a system has memory. We'll be interested in determining whether or not a system is causal. But those are additional properties. But to apply most of the theory that we'll learn in this class, it applies to linear, it's restricted to linear time invariant systems. It'll apply whether or not the system's causal, whether or not the system's stable. Again, those are different characteristics, but for all the work we do, it's restricted to these LTI systems. So this is our general notation. Block diagram notation. So we'll take first a look at why this is so important, at least why linearity is so important. So I'm going to draw a simple circuit here, just an RC circuit. With input X of t, and then we're taking as our output the voltage across the capacitor. And let's say the input is a unit step. It goes from 0 volts at time t equal to 0. We turn it on, and it switches to 1 volt. So our input looks like this. It's 0, and then 1 volt, x of t. The output, y of t, in this case, because the input is a unit step, the output, another term for it is the step response, or the unit step response. So sometimes it's called y of step. At least that's the notation he uses in this book. Some textbooks call it g of t, or the step response. And I'm not going to solve this circuit. It's the circuit you actually solve back in circuits 1. We'll learn some much simpler techniques for circuit solutions in this course, okay. But I'm just going to give you the solution. Initially, it's assumed that the capacitor is uncharged. We know when we switch this thing to 1 volt, after some period of time, the capacitor voltage is going to increase from 0, and it ends up at 1 volt. Okay? After a long period of time, there's no current, there's no voltage across the resistor, and the capacitor voltage is 0. So we know y of t is going to go from 0 to 1. And it does so according to this expression. 1 minus e to the minus t over tau ut, where the time constant of this circuit is the product of R and C. Okay, so what this thing looks like, it is 0 until we turn the voltage source on, and then it rises from 0 and then approaches 1. Okay, and that's what this expression says. At t equals 0, e to the 0 is 1, so 1 minus 1 is 0. And then as t gets larger and larger, this exponential term fades away, and then the term in brackets then just becomes 1. So this is what y of t looks like, or what the step response looks like. And the point of this example is not to get the solution, but to see if we could actually use that solution to find the solution for other inputs. And so the question is, can we find the response to a completely different input? X of t looks like this. Or in other words, we spent some time writing signals as, a sum of simpler signals. In this case, we could write this as 2u of t minus 2u of t minus 2. Right? Everyone agree with that? That's just twice a unit step minus a delayed unit step. Now, if the system is linear, okay, and this circuit is linear, then what that means is, we can find the response to a sum of inputs. That response is going to be equal to the sum of the outputs for the individual inputs. Now, in circuits, you call that superposition, actually. So here, what I'm saying is, if the circuit is linear, that is that the output is the sum of the outputs due to different inputs. And then the time invariance has to deal with the fact that, if the output if I delay the input by 2 seconds, which is what this part is the output just delayed by 2 seconds? That's the time invariance. That's the other key part here. But if both those conditions are true, then the output to this input is 2y step of t minus 2y step of t minus 2. Okay. And what that would look like, if I could try and squeeze it in here, you know, this, you know, got this thing minus this thing delayed by 2 seconds. And then, you know, I'm subtracting one from the other. So it's going to look something like this. And then 2 seconds later, I'm going to start subtracting it. And this is, and reach a height of 2 here. So it's a pretty simple example, but the concept's pretty powerful. There's all types of, you know, waveforms like this that I could construct. You know, I could construct a periodic rectangular waveform. I could just construct, you know, anything that looked like this. You know, just a sum of different blocks and find the output. You know, if I write the input, express the input as a sum of shifted unit steps, amplitude scaled, time shifted unit steps, then the output is going to be the same time shifted, amplitude scaled step output. So it's a powerful concept that will, again, rely on our circuits having this property throughout this course. So let's look at it in a little more detail. In particular, I'm going to look at, in more detail, both linearity and time invariance, what that means. So given, let's say I've got a system with input x1 of t, and it produces a certain output. I'm going to call it y1 of t. And y2 of t is the response to another input that I'm calling x2 of t. It's linear, the circuit is linear, or the system is linear, if the response to, if I multiply x1 by some constant c, then the output is increased by that same factor. So a system is linear. If I double the input, that produces a double output. That's called the scaling property. And then the other property is if I apply the sum of x1 of t and x2 of t, then I get the sum of the individual outputs, y1 of t and y2 of t. And if we've got a linear system, then we can use superposition to analyze the system. Okay, so kind of what this first one means, we can represent it in block diagram form. You know, if I have x1 producing y1, then if I run x1 of t through an amplifier to produce cx1 of t, and then now run that through my system, that produces some output called t cx1 of t. Right, that's what my system does, is it does some transformation on the input. In this case, the input is cx1 of t. If that's exactly the same as if I have my original x1, run it through the system, same system in all three cases here, and then scaled that output. So this is y1 of t, this is amplifying by c, this is cy1 of t. If these two are equal, then the system satisfies that scalability property. So that's what this is saying. If cy1 of t is equal to the transformation on this different input, then it satisfies the scalability property. And we could do a similar block diagram for, you know, the sum here. Time invariance is the other one. And mathematically, it says that, again, with input x of t, our system produces output y of t. The system is time invariant if we delay the input, you know, by delta, t minus delta. That produces a delayed version of the output. So the picture is almost the same here. Instead of amplification, I'd have a delay element. Delay the input produces, you know, this is some transformation on the delayed input. If that's equal to, you know, the output, the original output delayed by 2 seconds. So, I mean, that's the mathematical expression. What it kind of says from a circuit standpoint, you know, if I come in here and I hook up a function generator at a certain amplitude, at a certain frequency, or I switch on my DC supply, and I measure the output of my circuit, and I get some output, time invariant says if I come in next week and do that same experiment, same function generator settings or same DC supply settings, I should get the exact same output. Generally, that will be the case as long as my system doesn't have time-varying components. You know, as long as, you know, maybe it's an RLC circuit. You know, if the capacitor somehow, if the capacitor value is changing in time, I wouldn't expect to get the same output next week as I get this week. But for most of our circuits, most of our systems, as long as the components aren't time varying, then whatever output I get today, you know, I expect to get that same output next week to the same input, you know, as long as the system doesn't change. Okay, so that's what time invariance means, kind of in words. So it can be a little confusing. Let's look at a system. And mathematically, what this system does is when we apply x of t, the output is amplitude scaled by 3, and then it delays the input by capital T seconds. That's what my system does. This is an equation describing what my system does. So the question here is this a linear system? So another way to write this is what Tx of t is in this case is 3x of t minus capital T. So the question is now, if I scale the input, what is the output of my system? What my system does is it takes the input, which is now Cx of t, and it delays that by capital T. It might help to actually, you know, call this a new signal, maybe W of t. W of t is equal to Cx of t. And then what I would get out here is 3 times W of t minus capital T, and then substitute back in that W is actually equal to C times X of t. So this is the response I get due to the input scaled by C. Okay. To find out what my scaled output is, I go back to my original expression. This is what y of t is. Mathematically, cy of t is just c times this. Question is, are these equal? They are, they're mathematically equal. Actually, this is such a trivial case. So this satisfies the scalability property. We can go through and show that it satisfies the additive property as well. This is such a trivial case that it's almost like, don't all systems do that? Well, no. Let's take a look. Should call that one A, I guess. Might expect that this one's not going to be linear, because the output is proportional to the square of x, right? So let's see if this, in other words, whatever my input is, my system produces, squares it, and then multiplies it by 3. Okay. So let me take this other approach where I do define a new signal. Let me define a new input, Wt, that's equal to Cx of t. Okay. So what's the output due to this new input? My system squares the input, multiplies it by 3. That's how I define my system. So whatever the input is. So in this case, I'm going to get 3w squared of t. Now I can substitute back in. W of t is c x of t, so I get 3c squared x squared of t. Now, what is cy of t? Y of t was the response to my original x of t, the unscaled version. This is scaling the output. So this is going to take this original output and multiply it by c. So I get c3 x squared of t. This is doubling the output. This is doubling the input if c is 2. Now the question here is, are these equal or not? One has a c squared, one has a c. So again, a simple example. Let's just say x is 1. When x is 1, what I would get out would be y is equal to 3. Right? Now, let's take the case where I double x. So instead of x being 1, x is 2. What is my output then? Well, 2 squared is 4 times 3, I get 12. Okay, I've doubled the input, I get 12 as an output. Now, what was my original output with x equal to 1? It's 3. If I double that, what I get, 6. Is 6 equal to 12? No. So this is not a linear system. So again, generally, if you have some sort of something to a power, square root, something like that, it turns out even a linear equation this is not a linear system. You recognize that as kind of the equation of a line, right? How can that not be a linear system? It's because of this B offset. If you go through the proof here, you can show that this is not, without the B it is, okay, without that offset, okay. Again, let's take the case, make things simple. Let B and C both be 1, Okay. Let's let X be 1, the output's 2, right? If I double the input, so that X is now 2, what's the output? 3. Well, what if I doubled the original output, which was 2, right? I get 4. Again, they're not equal because of this offset. Again, without that, it is a linear system. So it's not always intuitive. Let's look at one. Let's go back and look at this, though. And this can be confusing. Yeah. Is this time invariant? It's a completely different question. Okay. Is it time invariant? So again, my system definition, what my system does is this. Okay. Now what I want to, my test now is I delay my input. I'm going to apply a delayed input. So let me call that a new signal, where I'm going to apply this delayed input to my system. What do I get out of my system? W of t. Well, all my system does is squares the input and multiplies it by 3 for any input. Now, if I make this substitution back in terms of x, I get 3 w squared t minus delta. Okay. I've gone back to the x. Oops, I didn't. I've gone back, substituted for w of t is x of t minus delta. Now, what is y of t minus delta? Well, this is y of t. So what would that look like delayed by delta? I substitute t minus delta in everywhere for t. I get 3x squared t minus delta. And they're equal. So this would be a time invariant system, but it's not linear. So I guess we have to look at one that's not time invariant, or it's time varying, but often I would just call it non-TI. So in this case, with this, we call the output t x of t. Okay. Maybe I'll try some pictures. Let's say if x of t is equal to 1, let's say x of t is equal to the unit step. Okay. Then what y of t would look like is just t u of t, which means it would be this, right? That's the unit ramp. This is what y of t would look like. Everyone okay with that? Y of my system just multiplies my input by t. Okay, my input now is a unit step. So for all t less than 0, unit step is 0, that product is 0. For t greater than 0, my unit step is 1, so I'm just multiplying it by t. Okay, now what does y of t minus delta look like? Well, we know what that looks like, right? It's just this thing shifted to the right by delta. That's what the delayed output would look like. This is y of t minus delta. Okay, taking my original output and delaying it by delta. Now let's go through this process of, okay, if my system is time invariant, if I delay the input by delta, I should get this same output. In this case, W of t is U of t minus delta. So instead of, my unit step input, x of t, what I'm doing now is delaying the input by delta. This is W of t. What does my system produce? What's the output to this? It's just t W of t. Now, what does t W of t look like? And we can make this substitution. Well, this W of t is just x of t minus delta. Over here, what's the delayed output look like? This y of t figure, I actually y of t minus delta figure. I go back to my original y of t expression and I substitute t minus delta in for t everywhere, and it's t minus delta x of t minus delta. Okay, so this is kind of the mathematical proof that these are different. Okay, but let's look at it graphically to see why they're different. When the input is a unit step, this is the output. This is the delayed version of the output by delta. When the input is a delayed unit step, what my system does is multiply t by this picture. Okay, t is just a straight line, right? So, but it's going to be 0 up until this point because my delayed step is 0. And then now this is 1, I multiply it by t, so this is actually going to jump up immediately to delta, right? Because t is equal to delta. And then for all t greater than that, it's going to look like that. So are these two pictures the same? The answer is no, they're not. Okay. This is not a time invariant system. You'll have this anytime like any of your coefficients involve time. Okay. Again, most of the systems we work with are, we'll have these differential equations from our circuits that involve the R, L, and C. If any of those quantities, if the resistor was time varying, we would expect, if the resistor is 1K this week and it varies in time and it's 2K next week, we're going to get a different output next week, right? But ideally, if the resistance component and inductance values all stay the same, we should get the same output next week, just delayed by a week to what we would get for that same input this week. So these can be a little head scratching, as you work through these. It gets so draw plenty of pictures. The circuits we work with are all described by linear constant coefficient differential equations. Those are linear and time invariant. Okay, if you get time varying coefficients, like a coefficient that has a t in it, that would correspond to a time varying. But all the circuits we work with, would be something like 3 some voltage second derivative plus first derivative, where if we're interested in some output voltage plus 10 V of t. Maybe this is a voltage across a capacitor somewhere in a circuit is equal to, so let me put little C's on here because these are capacitors. Maybe, some applied input voltage would be the corresponding differential equation. But this is a linear constant. So the linear part means none of the VCs or the VIs are squared. Okay, we've got second derivatives, third order derivatives, that's okay. None of these derivatives are squared. Okay. So it's a linear differential equation because all the terms are first order. And it's constant coefficient because coefficients are 3, 1, and 10. So none of the if this were like a 10t or a t here, or a t squared, then it wouldn't be a constant coefficient. But all the circuits you work with, all the RLC circuits that you worked with, actually can be expressed as a linear constant coefficient differential equation. We don't want to solve differential equations. No one likes that class. Differential equations are hard, right? We spend this entire semester looking for alternative techniques to solving differential equations. So and that's our transform techniques. Okay. A really important signal for us is the impulse and the corresponding response to that impulse. So if we've got an LTI system, we're going to use special notation when the input is an impulse. In this case, instead of calling this y of t, we call it h of t. So h of t throughout this course will indicate that this is the response to an impulse. Now again, an impulse is kind of this fictitious signal. I can approximate it in the lab. I can't generate it, but I can mathematically find out what it is. You know, theoretically, I can calculate what the impulse response is in my system, and we'll figure out how to do that. Generally, if x of t is u of t, the output is what we call y step, the step response. Since differentiation and integration are actually linear operations, I'm not going to prove this, but remember the impulse is the derivative of the unit step. The impulse response is the derivative of the step response. So this would be one way to get the impulse response. If I can find the step response, and I can generate a step in the lab, that's a perfectly normal signal, right? It's just 0 and then goes up to 1. So if I can find the output to a unit step, the step response, I can take the derivative of that to get the impulse response. We'll see that the impulse response actually allows me to find the output to any input. That's why it's so important to us. We use it throughout the semester. We either use the impulse response or its transform. That's called the frequency response of the circuit, or it's also called the transfer function. Okay? But this is fundamentally important to us. This h of t will actually allow us to calculate the output of a circuit to any input. And then similarly, the step response can be found by doing this running integral of the impulse response. Okay, so I can theoretically find the impulse response of that RC circuit we started with. Find h of t for RC circuit. Y step of t, we had for that 1 minus e to the minus t over tau u of t. Okay, so I'm going to take the derivative of that. So h of t is the derivative of 1 is 0. The derivative of e to the minus t over tau with respect to t, I just have the minus 1 over tau that I pull in front. it's 1 over tau e to the minus t over tau u of t. Okay. Now, am I done? The fact that I'm asking that question probably gives you a hint that I'm not done. What did I mess up? Doesn't u of t have a derivative? It does. It's our delta. Okay, so I'm not done. I have to actually use the product rule here. This is a product of two functions of time. So I took the derivative of the first times the second. Now I've got to take the first times the derivative of the second. So this is the impulse response of the circuit. Now this simplifies a little bit. Okay. If you remember last time we had or maybe it's the time before last, we had this multiplication property of the impulse. In particular, if it's not, that's just a special case where it's not, the impulse is not delayed. Okay. This is called the multiplication property of the impulse. Anytime you've got an impulse, look to see if it's multiplying, some function of time. In that case, I can simplify that function by just evaluating it at the location of the impulse. Okay. And I've got that here. I've got an impulse multiplied by a function of time. So this simplifies. What value of t do I evaluate this at? Where's the impulse located? It's at 0. So if I plug in t equal to 0 here, what does this term in brackets become? It becomes 0, right? I'll have e to the 0, 1, which is 1. 1 minus 1 is 0. So this becomes 0 delta t, which it actually does go away in this case. Okay. And so in this particular problem, it reduces just to that derivative of the first part times u of t. That's not always true, though. So you got to be careful that you use that product rule. The derivative of the unit step actually has meaning for us here. And this is actually the impulse response of that circuit. And we'll see that you can actually use this impulse response to find the output to any input. One final thing, I'll let you go. The response of any system to a short pulse, let's say it has duration t and area A, is approximately A times h of t. As long as the pulse is short enough, and this is really just, I'm saying that my short pulse is a scaled version of the impulse. It has a weight of A instead of 1, and so my output would be be scaled by A. So regardless of the pulse width, if I can find its area, I can get an approximation to what the output looks like. And we'll use that property. I think next time we'll turn this around and start figuring out how do we actually find the output for other inputs. That's it for today. Which symbol?
The y of t something,
Yeah.
h of t over here, that you just wrote.
Approximately
Okay.
two squiggly lines.
I mean, I don't know that they're accurate.